So this little part of the lesson, you've already, if you're at home, you've already done the ed puzzle, and in class, we've already done the lab. So we're talking about things that are exothermic and things that are endothermic, okay? Exothermic, when we talk about something being exothermic, we talk about it having a negative delta H. Delta means change, H means heat. So something that's exothermic is losing heat. It has a negative delta H. You need to know that. Something that is endothermic, that feels cold, heat is going into it. Even though it feels cold, heat is going into it. It has a positive delta H. Okay, and this is related to when the drawing I made of the finger, when you're touching something. If you're touching something and it feels cold, then the heat is going out of you and into it. So look, endo, exo. Here's a test tube. Here is your finger. If you're touching a test tube and it feels hot, the heat is going out of it. So inside the test tube, it's losing heat, negative delta H. That is exothermic. Endothermic means you're touching it, it feels cold because it's sucking the heat out of your finger and it's actually gaining heat energy. What? Mr. Perkins, this reaction that feels cold is gaining heat energy? Makes sense? All right, let's keep rolling. Now, when we talk about this, we have to think about the potential energy. Okay? We're talking about the energy in the system. There are a couple of terms we need to know. And the one that I want you to know is activation energy. Okay? The energy needed to initiate a reaction. And you may be saying, well, Mr. Perkins, a lot of reactions just happen. They're spontaneous. True. True. That means they're spontaneous at room temperature. Would any reactions happen at absolute zero? No. So there has to be some energy somewhere, right? All right. So the activation energy is the energy needed to start a reaction. Now take a look at this. I love this picture. This picture explains everything and every question that could be on your test about this. Okay? And if you'll watch this, this will definitely help you do the worksheet you're about to have. Ready? This is the amount of energy in the reactants. It's up here. Okay? And then later, after the reaction happened, the energy level is way down here. So our first energy level is up here, right? And then our later energy level is down here. Has this thing gained or lost energy? As time goes by, as the reaction happens, the energy level goes from up here to down here. So has it gained or lost energy? If it lost energy, then it must be exothermic. This is an exothermic reaction. Does that make sense? Okay. Now, let's go backwards in time, and let's look right here. We're going to go backwards. If I go backwards to right here, has anything happened yet? No. No. But if you look carefully, before you can go down here, you have to go up. This amount of energy needed before we start going downhill is the activation energy. Where did the activation energy come from? It could come from your hand. Maybe you're holding this and it takes heat from your hand to start the reaction. It could be energy that's already in the water. We could have warm water, right? So this reaction is exothermic, and it requires this much activation energy. Simple enough. All right, check this reaction out. Check this reaction out. In this reaction, the reactants have very little energy. And then after this chemical reaction has occurred, there's more energy. So this reaction must be what? Did it take in energy or get rid of energy? It took in energy. This reaction is endothermic. Okay? This is an endothermic reaction. Okay? So, in order for us to get from here to here, it took this much energy. This tall line is the activation energy. And let's say this was like, I'm going to make up a number. This is like 100 kilojoules. I'm just making up numbers. And then this was 300 kilojoules. Then the activation energy was 200 kilojoules. Does that make sense? The difference between 1 and 200. Are you with me? Okay. And then another thing we need to look at is what was the actual heat gain in the system? Well, the actual change in heat, the delta H, remember, delta triangle means change. So the change in heat energy in the system was only from where you started to where you ended. So the delta H is only this high. Does that make sense to you? The activation is this high. The total gain is only this high. Right? And what is something we could throw here to make this happen faster? What's something we could throw in here in the reaction area to make it happen faster? To not change anything, just to make it happen faster. A catalyst. All right? So that leads us up to this. Boom. Here is a catalyzed reaction. A catalyzed reaction. Ready? A catalyzed reaction looks like this. This is what happens without a catalyst. You need all this activation energy, okay, in order to start going downhill to the product. But if you have a catalyst, you only need this much activation energy, okay? Now, did this catalyst make the reaction happen faster? No. It just made it happen more easily. People at home, watch this. And again, this will be on a worksheet. We'll show you answers on the worksheet. Most catalyzed reactions look like this. They actually, and this is what it looks like on the worksheet, actually take less energy, and guess what? They go ahead and happen faster. Do you see how this one happened fast? If this is time going by, right? Then this one, with the catalyst, takes less activation energy and gets to where it's going faster or sooner. Does that make sense? This is what we think about when we think about a catalyzer. Not only changing the amount of activation energy you need, but also making it happen faster. What do you think about that? Does that make sense? Right, this is what your worksheet looks like. I'm going to tell you one more thing, and this is for you and everyone at home. What are some things that we do to make a reaction happen faster? And this is on the test because this is mostly just common sense. In our test tubes, in our reactions, what are some things we can do, even when we're cooking, to make things happen faster? Ready? 1, put more stuff in. Increase the concentration of the reactants. And this will be posted also in your notes online. 2, if you're trying to make gases dissolve, like according to Henry's law, then increase the pressure. if you're trying to make gases react with each other? Because if you increase the pressure, won't they collide more often due to collision theory? Okay, and this is the hardest one to remember. This one right here. Whoops. Number 3, increase the surface area of the reactants. What does that mean? This is why all the solids that we dump into water are all in what form? What do all those solids look like? They look like this. What's this? That's right. So people at home, we use fine powders like this because each little grain can be surrounded by the water, right? That's increasing the surface area. Does that make sense to everybody? Increase the temperature. You know, now this will be not always hold true for an exothermic reaction. Increase the temperature. And then add a catalyst. And in biology, you always talk about this catalyst. There's a catalyst that's in your saliva that makes your food easier to dissolve. Does that make sense? You probably talked about that in biology class. So, increase the temperature, add a catalyst, increase the surface area. This is the one that may not be as intuitive for you, increase the pressure, and then put more junk in it. So let's say you're dissolving something, or you're cooking at home, and you want to increase the reaction rate, right? Well, throw more stuff in there, heat it up, make sure the stuff you're trying to dissolve is a powder. Right? That's it. I can't think of anything increasing the pressure would be in cooking, unless you're using an Instant Pot, but you're not really trying to cook things and dissolve gases into them. But those are how you do it. So that's it, people. You already know collision theory. That's it. You're going to have a worksheet on this activation energy, and we'll also post the answers eventually. Okay? All right. For you people at home,